Hello everyone, and welcome to your 6th lab. In this lab, we're once again going to be working with our FPGAs. And for this lab, we have two tasks. Part 1, called a 7-segment driver, and then Part 2, Introduction to CPU Design. So for the first part, we're going to give you a segment of a code which you are going to complete. This code that we are going to give you displays numbers on what we call 7 segments. Now, 7 segments are usually like this. They are used to display numbers, and they, as the name implies, have 7 segments. And each of these are labeled as A, B, C, D, E, F, and G. We're going to use these LEDs, these 7 segments, to display some numbers based on our input. So for this case, the input is going to be our switches. And let me actually show you the design through virtual FPGA. So I'm now going to run virtual FPGA. So I have my virtual FPGA open. Now I'm going to add the code that we give you. So I say add, and then I navigate to our lab, and I'm going to add 4-digit 7 segments and its wrapper as well. So top wrapper 7 segments. And now let's see what this code does. It's gonna take a while. And there we go. So now our code is running. So the important components for this particular task are the switches and the 7 segments. And what this code right now does is, when I flick this switch here, this input is going to change. But how does it change? So what this currently does is it uses these switches to determine this number. And if you think of the switches as a binary number, and think of switching as switching from 0 to 1, this is exactly what it does. So right now I have 0, 0, 0, 0, 0, 0, 0, 1, which is 1. So it displays a 1. If I wanted to display 2, I would flick the second switch. 3, and like that. So right now, this only displays values from 0 to 3. If I tried to switch this, nothing would happen. So I should be seeing 4 right now, but nothing is happening. And that is exactly what your task is. So in this task, we want you to complete this code to have it display from 0 to 15 instead of 0 to 3. So in this case, we want you to use these 4 switches to display up to 15. And why up to 15? Because in hexadecimal, that is the largest number you can display in a single digit. So you will be using these 4 switches to display the number right here in the 7 segments. And let's actually take a look at the code and see how we're supposed to accomplish this. So this right here is the code we give you. Sorry, not that one, this one. There we go. And what you have to do is you have to complete this part. In fact, let me enter this here. Complete this. So as you can see, right now, our case statement has values from 0 to 3, and you're going to add the rest of these. So for example, 4, you're going to do something here, and then 5, you're going to do something here, and so on and so forth. And of course, how are we going to do this? So these numbers actually represent something, and that something can be determined from this figure right here. So let me put these side by side. All right, so let's take a look at this. So for example, 0. What would you have to do to display a 0 on a 7 segment like this? So let me actually take a screenshot of this and then show you, right? So here, let's take this figure. If I want to display a 0, I would enable this one, this one, this one, this one, this one, and this one. So A, B, C, D, E, F. I would only have the G segment disabled. And let's actually see how this is reflected in the code, right? So here we have the 0 value. And what we do is go from the least significant bit, meaning from the rightmost bit to the leftmost bit. And this is A, B, C, D, E, F, G. So as we said, from this picture here, we had to enable A, B, C, D, E, F, but disable G. For that reason, we've kept A, B, C, D, E, and F as zeros, and G as 1. Meaning that when you write a 0 to a digit, that means the corresponding segment will be enabled. It'll be turned on. When you write a 1 to it, it will be disabled. And also, you might notice that we have an 8-bit number instead of a 7-bit number, but we have 7 segments here. So the last bit, the most significant bit right here, actually corresponds to the decimal point here. Well, not point, just decimal, this point right here. So as you can see, there is actually a point display here. Maybe you can see better from this display here. So if you want to enable this, you write a 0 to the most significant bit. For the sake of this lab, you don't have to enable this, so just keep this as 1. But if you were to take a look at the other examples, for example, like 1. So for a 1, what would I need to do? Let's see. So let's erase these. For a 1, I would enable B and C, and everything else would be disabled. And let's look at our code. So A is enabled, B and C are disabled, and the rest are also disabled. So this is how I display 1. And similarly, you can take a look at 2 and 3. They're going to be similar. You can figure those out yourself. So all you need to do for this part is just complete this case statement. One more thing that I will mention here is this anode here, and which is also an output of our module here. So this anode here determines which segment you're going to use on your FPGA. So if you look at our FPGA here, so let's just use this image right here. We want you to display the results in the rightmost digit. So in order to do that, you use the anode value, and it's actually fairly similar to how we use the 7 segments as well. So in order to use the rightmost digit, what you're going to do is say 1110. So this means enable the rightmost digit and disable the rest. So fairly similar to our segments actually. And other than that, we've also given you the top wrappers, so you don't really need to change anything here, but you should of course take a look at them. So for this case, you're going to have your clock as usual, your switch input for your switches, the anode, the one we just discussed, the segments, this is the output for determining which value you're going to display, and of course your reset, which is binded to your rightmost button. And that's it. And let me actually show you what that is going to look like. So I will remove the file and I'm going to add the finished version, this one, and I'll start. Again, it's going to take a while. There we go, it started. So as before, I can write 1, 2, 3, but also 4, 5, 6, 7, 8, 9, 10. So for 10, of course, I don't write a 10, I write A, because in hexadecimal, 10 is A. And let's continue. 11, 12, 13, sorry, I skipped one, didn't I? 12, 13, 14, and 15. So this is how your first task is going to look. And with that, let's finish this one. I can stop the program now. Okay, so that covers the first task. Let's look at the second task. So in this second task, what we want you to do is a very simple CPU design. And this CPU can only do 4 operations: addition, subtraction, multiplication, and a bitwise OR operation. And how it's going to do this is through your switch inputs once again. And let me actually just show you through this image here. So as you can see, we have our virtual FPGA once again. So each of these switches actually correspond to a value right now. So just as before, our result is going to be displayed in our 7th segment. And I'm going to take my input through the first 4 bits, the first 4 switches. The first 2 for input B, and the second 2 for input A. And then the next 2 switches are not important. And then the last 2 switches are for opcode. Now, if you should be familiar with the term opcode from very simple CPU. They actually refer to these values that we have given you. So a 0 as an opcode refers to an addition. A 1 refers to subtraction, 2 to multiplication, 3 to bitwise OR. So if I were to, let's say, have this switch disabled and this switch enabled, I would get a 1. So I would do a subtraction. And what would I subtract? I would subtract the value I get from A from the value I get from B. So let me actually run the project and show you how it looks. So this is the completed project. So if you try to run the one that we give you, nothing actually is going to happen. And then top wrapper CPU 7 segments. I'm going to run this. Let's wait for it to compile. And there we go. So let's actually keep the opcodes here. So, okay, let's try a simple operation. Let's try 2 plus 2. So how would I do 2 plus 2? So since I want to do an addition, I'm going to keep these as 0. And then to enter 2 plus 2, for B, let's enter 2. And for A, let's enter 2 as well. And 2 plus 2, we get a 4. So now let's try a subtraction. So for subtraction, we're going to want an opcode of 1. So 1. And then let's say I subtract 1 from 3. So let's set A to 3 and B to 1. So 3 minus 1 is 2. There we go. And next we have multiplication. So for multiplication, a opcode of 2. And let's do 3 times 3. So 3 times 3. 3 times 3 is 9. And finally, we have the bitwise OR. So for bitwise OR, I'm going to want an opcode of 3. And let's do 2 or 1 is 3. So here I have 1 0, which is 2, and then I also have 0 1. And if I OR these two, what do I get? So 0 0 is 1, and 1 0 is also 1, so I get 1 1, which is 3. And there we go, we have a 3. So with that, that actually completes this part as well. So let's actually look at your code for this part as well. So here we have a very simple code that we gave you. It's actually fairly simple to the last part that we gave you, if you look at here. But the difference is we don't have a always at pos clock statement here. That is because we do not actually need this statement. It's because for this part, you don't actually need to preserve any values, meaning that you don't really need any flip-flops. That's why we don't actually need this always at pos edge right here. And other than that, again, we have a case statement for displaying your result. And what you can actually do is you can actually copy this case statement from your previous lab, right? So if you completed this, you can just copy in the inside of this statement right to here. So because this display is going to be the same. The only difference for this case statement is going to be, of course, this here. So here we have the result here, and here we have the segment decimal. So for this lab, what you need to do is you need to generate this result value so that we get the correct display on our FPGA, on our 7 segments. So use the switch input to come up with the result value, and that's it. And of course we have this anode value as was discussed in the previous part, so this is just used to determine which 7 segment you're going to use, so you don't need to change this. Just keep this as it is. I believe that is it. So of course we also want you to synthesize your code and send screenshots again. So the screenshots are going to be the same as the last time. We want you to take the screenshot of your warning screen after you've done your synthesis. So you're going to do this for both of your labs. So for submission, you're going to send your Verilog files and your synthesis. And that about covers it.